Welcome to Challenging Climate, a podcast where we discuss the science, technology, and politics of climate change. I'm Jesse Reynolds, an environmental policy expert.
I'm Pete Irvin, a climate scientist. Each episode will bring in a guest with a unique perspective and deep expertise on climate change and put challenging questions to them.
In this episode, we spoke with Dr. David Fahey. He is director of the Chemical Sciences Laboratory in the U.S. National Oceanic and Atmospheric Administration, known as NOAA, and he also serves as co-chair of the Montreal Protocol's Scientific Assessment Panel, which produces a quadrennial assessment of stratospheric ozone depletion.
Now, this episode was recorded with just Jesse, but our guest, I think, more than makes up for that in that he spans both the science and the policy, working as he does with the international group that's trying to deal with ozone. But he spanned also three topics, starting with sort of the history of stratospheric ozone, going through climate change, and thinking about stratospheric aerosol injection. And in particular, it was exciting to hear about two big new reports that link this together. On the Montreal Protocol put for the first time stratospheric aerosol injection in its assessment, in its quadrennial assessment report of the Scientific Assessment Panel to the Montreal Protocol on ozone depleting substances. And also he was involved with the United Nations Environment Programme's new report that also included SRM, an independent expert review on solar radiation modification, research and deployment.
We'll have links to both of those reports in our show notes, of course. What interested me about speaking with Dr. Fahey is that the challenge of stratospheric ozone depletion, when I first became interested in environmental issues around, let's say, 1990 or so, loomed large as the greatest, most complicated threat to sustainability. And since then, it's been pushed aside a bit, largely by climate change, but also by biodiversity, in part because those issues are big, but in large part because the efforts to reduce the destruction and, in fact, allow the recovery of stratospheric ozone have been quite successful. And it's often held up as a model. What can we learn about the destruction of stratospheric ozone for climate change? And this science policy interface has been key to that. The Montreal Protocol Scientific Assessment Panel is a bit analogous to the Intergovernmental Panel on Climate Change, but it operates differently in key ways. And in our next episode, we'll touch more on the IPCC process with an author from there. And I'll also say that this other report that we discussed, the UNEP report on solar radiation modification, it strikes me as a big step. It's the first scientific report dedicated to SRM from an intergovernmental organization. And in that sense, it's key. And that's the topic of the back half or last 1/3 or so of our conversation, where we get into the report and some of the questions that they went through, some of the conclusions they were reached, and ultimately focusing in around on the real importance of thinking about solar radiation modification balanced with the risks of climate change. And this podcast, like our other episodes, is produced by Jillian Chong. Please help us cover her and our other costs by supporting us at patreon.com/challengingclimate. That is patreon.com/challengingclimate. And now for a conversation with Dr. David Fahey. Joining us today on Challenging Climate is David Fahey, Dr. Fahey of the podcast. Let's begin with a word about your background. How did you transition, let's say, what was the path from high school to where you're at now?
First of all, Jesse, thanks and Peter for inviting me to this podcast and seeking my opinion on these topics. So I studied physics in high school and it kind of stuck at that point, fascinated by it, and it was difficult. So I like difficult things. Went on to college and majored in physics at the University of Wisconsin in Madison. Went to the University of Missouri because there was a good collaboration between Wisconsin and Missouri. Studied atomic and molecular physics, got a master's and PhD with Professor Laird Shearer, who developed a magnetometer that finds submarines under the water for the military, and then came to Boulder at his recommendation, actually, to work in what was known then as the Aeronomy Laboratory, which is the predecessor of the lab that I run today called Chemical Sciences Laboratory. And so they were invested in understanding the ion chemistry of the upper atmosphere. And the ion chemistry of the upper atmosphere controls how radio waves bounce off the ionosphere. And so it was a very practical aspect. A lot of complicated chemistry up there, and the way we did it before my time was to simulate the reactions in the laboratory so that we could put together an entire scheme of what's going on when all of these reactions go on at the same time. And that work was centered on a device called the flowing afterglow, which is an exceedingly flexible device to do reactions. Molecule A reacting with molecule B, one of them being ionized, going to another two molecules. And so there was a compendium of hundreds of reactions that were relevant to this part of the atmosphere. So anyhow, I drawn into that as the next postdoc, so to speak, which was quite an honor, I would say. And at that time, the ionosphere chemistry was kind of reaching a level of completion, like we think we understand everything we need to know. And being in NOAA and the government, we moved on to call the next problem, which was acid rain at that time, bringing us down into the troposphere instead of the upper atmosphere. And so started working on gas phase measurements in the troposphere, initially related to acid rain. And so that led to the development of a new technique called the reactive nitrogen catalyst technique, or NOAA, where we could take an air sample and determine how much reactive nitrogen was in that air sample in real time. And so this was somewhat revolutionary at the time, given the other techniques that existed. We made some of the first measurements with that device up here in the foothills west of Boulder. But then it became very interesting to actually measure reactive nitrogen in the stratosphere. Very undersampled region. It's still undersampled. And so I got drawn into a NASA-based program, collaboration with NOAA, to make a measurement of reactive nitrogen on board high-altitude research aircraft, in particular the NASA ER-2 high-altitude aircraft. That was pretty groundbreaking stuff at that time, because there's the in situ measurements, meaning going to the stratosphere to make a measurement of what was there, just didn't happen very often and hadn't happened on board aircraft. And so was left to do it with altitude balloons, which is an exceedingly difficult thing to do. And so we started making measurements of reactive nitrogen in a payload of other tracers, as we call it, in the stratosphere, to understand how transport worked in the stratosphere. Reactive nitrogen is a tracer of stratospheric air, meaning it's made in the stratosphere and much less abundant in the troposphere. So if measuring it gave you an insight into the history and the nature of the air you were looking at in the stratosphere. Then what happened, this was in the 80s, was there was a paper published that announced the anomalous depletion of ozone at high latitudes. This was by Joe Farman of the British Antarctic Survey, using measurements that he took himself by going to the ice and finding anomalous depletion in the early spring in the Antarctic, meaning September and October. So he published this in Nature and associated it with the rise in chlorofluorocarbons in the atmosphere, saying, this is how I think ozone is depleted. And nobody had anticipated the Antarctic ozone hole. We anticipated Antarctic global ozone depletion due to chlorine chemistry. This was pointed out by Rowland and Molina, who in the 70s, they eventually were awarded a Nobel Prize in the 90s. And so an alarm goes off in NASA and NOAA saying, wow, what are we going to do about this? There were three competing theories at that time. Only one included chlorine and bromine. And so NASA and NOAA worked together to actually fly into the Antarctic ozone hole and find out what was going on. And so my reactive nitrogen measurements were part of that. So in 1987, this aircraft went to Punta Arenas, Chile, and then flew this aircraft south into the Antarctic ozone hole as far as 72 degrees south. So that's 20 degrees of latitude. You can do that in 4 hours in an aircraft like that, and then turn around and come home. And so in August and September, we conducted 12 flights into the Antarctic ozone hole and developed a data set that's now still called today the smoking gun. where we had reactive chlorine measurements on board. This was from Jim Anderson at Harvard. Jim is still there. And the ozone came from Mike Profit, who was a member of this laboratory. These are in situ instruments, meaning they're bolted on the airplane. They sample air directly as the aircraft is flying along. And we found, as we went into the Antarctic ozone hole, chlorine going up, reactive chlorine going up, and ozone going down in a highly correlated manner. And so if you create the context of those measurements using the other measurements on board, which included my measurements, it was unequivocal evidence that reactive chlorine was destroying ozone and creating the Antarctic ozone hole. So these are really powerful measurements. They can only be accomplished by flying an airplane into that region. There were several brave men who chose to do that. They were all men at that time. And it was basically a bit of challenging your fate, because if you had an airplane with one engine at 72 degrees south and that engine decided for whatever reason not to operate, you were basically not going to make it back alive. And so it was a gutsy thing to do for everybody involved, but particularly the pilots. So I measured reactive nitrogen and basically could demonstrate that there were particles formed in the Antarctic stratosphere that contained reactive nitrogen, and that these particles actually sedimented out stratospheric region because they formed a particle and gravity then removed them. And so this removal of reactive nitrogen in the polar regions in winter was a new phenomenon. And I went on to measure that in the Arctic also. So doing basic science with a payload of instruments on an aircraft, a payload that's built by not only people in NOAA, but NASA and other organizations, is really the theme in my career. And it started there in full force in 1987 in the Antarctic. And listeners can go on our website and find out a lot of detail from that mission. You type in CSL, Chemical Sciences Lab, NOAA, NOAA, and AAOE, you will find a website that captures that mission, which isn't remembered necessarily, but that was the smoking gun mission. So, Jesse, that started me on another decade and a half of being involved with the high altitude aircraft, in particular the NASA ER2, look at the stratosphere in other places. We solved the Antarctic ozone hole, so to speak, at that time. And then we went to the Arctic because there was fleeting evidence that ozone was being destroyed in the Arctic in the winter. It's not as intense. We know that. We understand why, but we conducted the same set of measurements actually in 2 campaigns. And then we also did mid-latitudes, meaning ozone is depleted around the world, most intensely in polar regions. And indeed, in the 90s, we flew the Antarctic ER2 from the North Pole, literally, to 70 or so degrees south from New Zealand this time, and made measurements continuously over that latitude range. And that has not been repeated since then. And so my career has kind of been started there, and then I ventured out to other things like black carbon.
Let's jump in here. And before going too much further beyond stratospheric ozone, I want to hop back to the ozone layer, which is the topic of one of 2 reports that were recently released. And you talked about the work that you contributed to in the 80s, identifying the existence of a hole of a depletion of stratospheric ozone, and as well as evidence for the cause of that. And for listeners, stratosphere is typically the second layer of the atmosphere moving up from the surface. You have the troposphere, which is where we live and work, and generally where we fly passenger aircraft. And you go quite a bit higher than passenger aircraft, depending on your latitude. And then you're up in the stratosphere above where there's weather. So ozone there occurs naturally. Why should we be concerned that it's being depleted? Why not just let that process take its course?
Yeah, good question, Jesse. Basically, every country in the world wants to have an ozone layer overhead. Ozone in the stratosphere filters out harmful ultraviolet radiation from the sun that's always present. And by doing that, protects life as we know it, both ourselves and other animals and ecosystem and plants, etc. So all life on Earth has adapted to having an ozone layer. And so removing it, reducing it would be essentially catastrophic to life as we know it. And this has been recognized for a long time. And so what happened with the ozone hole is that humanity was put on notice that their activities summed over the world were actually real threat to the ozone layer. That once it was understood that Antarctic ozone hole was caused by chlorine and bromine, and that the source of that chlorine and bromine were the chemicals that we were manufacturing on a large scale, using to our great benefit in refrigerators, etc., but then at end of life, releasing it to the atmosphere and allowing them to reach the stratosphere. That meant that we pay attention and not do that if we wanted to continue to have an ozone layer. So the science provided the insight into the cause. The Antarctic ozone hole is the largest manifestation of the threat of these chemicals to ozone. But throughout the planet, ozone was also declining. And so that's why there was a red flag raised by the scientists and ultimately was acted on by the Montreal Protocol.
So this would manifest as increased rates of cancer due to the incoming ultraviolet light from the sun, much of which is blocked out by naturally occurring ozone up in the stratosphere. And you mentioned the Montreal Protocol. That's one of the best known global environmental agreements, often touted as a model of success. It was implemented quickly, it gained global ratification, and had significant impact on the production of the chemicals that were depleting and still deplete ozone. Now, your work there has been part of the Scientific Assessment Panel, which just released its 10th scientific assessment of the state of ozone. Can you say a little bit about this assessment panel and how it interacts with decision-making by the parties to the Montreal Protocol?
Yeah, good question. The Montreal Protocol is the most successful environmental treaty in history, as you point out, by having every nation in the world agree to control the production and consumption of these chemicals called ozone depleting substances, which are synthetic gases that we manufacture. And so the success of the protocol, one dimension of that is the way it handled the scientific aspects of ozone depletion. And as you mentioned, the quadrennial assessment, this is produced by the Scientific Assessment Panel, of which I'm a co-chair. There are 4 co-chairs. And we do this every 4 years as a drumbeat to assess the state of affairs, so to speak, of ozone itself. What's it doing? And in the stratosphere, what are the trends showing? And ozone depleting substance. We know what they are. We measure them routinely in the atmosphere. How are they changing? And do we understand those changes? And then other topics in the recent reports of how climate change, which is brought about by greenhouse gases, how is that affecting the ozone story? So the Scientific Assessment Panel, well before my time, has delivered competent assessments to the protocol, often following their suggestions. They provide us what we call terms of reference, what they, as parties to the treaty, would like to see discussed or evaluated in our next assessment. So this has been a very competent aspect of the protocol, meaning their deliberations and their decisions are based on science as they need it. And it comes about in an automatic way, so to speak, meaning the quadrennial assessment can be anticipated that yes, within the next 4 years, there will be another statement from the scientist. So this makes the protocol deliberation process very sure-footed with regard to the science.
And that's the way that operates is a bit different than what many of our listeners, including myself, are more familiar with. And that's the Intergovernmental Panel on Climate Change, which preceded the agreements. The IPCC was established, my memory serves me right, in 1988, issued its first assessment report in 1990, which then in turn informed the first treaty, the UN Framework Convention on Climate Change of 1992. And not only is the IPCC separate from the climate change policy architecture, if you will, but governments have a more hands-on role, at least in the summary for policymakers. In fact, as we speak, the IPCC is meeting in Interlaken to approve the synthesis report, including the summary for policymakers. Given your experience, how would you characterize the key differences, or at least the key features of the Scientific Assessment Panel of the Montreal Protocol that help make it such what appears to be such an effective body?
Good question, Jesse. So the distinction is that the Montreal Protocol actually has regulatory actions associated with it. There is no such body or treaty associated with IPCC and the climate side. And so the success of the Montreal Protocol, if you examine it in detail, comes down to three dimensions in addition to the science. One is that it's multilateral, meaning every country of the world is at the table and has agreed to the regulations and provisions of the protocol. Second, it's legally binding, that the parties come together and they say, look, we want to make sure we all behave, and they have trade sanction processes that if a country goes rogue, there's some feedback and some pulling them back into the fold. And number three, it's fully funded, meaning they don't leave the developing world behind. If you make a technical decision, we're going to move from this compound and this compressor to another one, the rich countries can do that pretty quickly and effectively. The less rich countries can't. And that was recognized early on. And no one's left behind now, that the regulations are sensitive to the fact that different countries have different resources and they have different conditions, a country with a different climate. So that's been the effectiveness of the protocol. And we don't have that on the climate side. We have an outstanding scientific basis for regulations associated with climate in the form of the IPCC reports. They're fantastic and serve as a Bible of our Earth system, so to speak. How does it work? How might it be changing? How do we know? And you have hundreds of experts writing each cycle of it. But then there's no place to send it, so to speak. There is no protocol body that will do what the Montreal Protocol did for ozone and do it for climate. For example, we all know that the Paris Agreement is not binding. It's a voluntary process. And in the end of the day, it won't be as effective as one with legally binding provisions. So that's what I would call the major distinction. And as you pointed out, we're serving the parties to the protocol, but they are not involved in us writing our assessment or bringing our assessment to conclusion, other than providing us with terms of reference for what they would like us to write. I'm not absolutely sure why that is the case. The Montreal Protocol was the early adopter in terms of having this kind of arrangement. And in some respects, if it's not broken, don't change it. And so it's working extremely well at the moment from my scientific point of view. So those are some of the distinctions.
You mentioned that the ozone depleting substances have been phased out and substitutes have been developed over the years. And I've watched this process out of the corner of my eye. And my understanding is there's been 3 or 4 primary generations, if you will, categories of substances, starting with CFCs as the original leading culprit, gradually replaced by HCFCs, is my understanding, and then HFCs, each of which all of them, I believe, are chlorinated organic compounds. And my understanding is HFCs are now being phased out through a recent amendment to the Montreal Protocol. Can you elaborate a little bit on that process? I assume that each generation had less ozone depletion power, but it also interacts quite strongly with climate change. How has this played out over the last decades?
Yeah, another good question. In the early days, the protocol, the focus was on ozone and the ozone depleting substances that we're manufacturing and releasing, and we really need to stop. And so the initial provisions were focused on the ODSs, as we call them. And you're right, the first group was CFCs. They're the really potent ozone destroyers. And the decision was made to transition to an intermediate set of compounds called the HCFCs, as you pointed out, hydrochlorofluorocarbons, which still destroyed ozone, but much less effectively on a per molecule or per mass basis. But the idea going into HCFCs is that they would fill the gap between the CFCs and the HFCs, as you pointed out, and give the sectors time to adjust, et cetera, while we were reducing our impact and threat to the ozone layer. The HFCs, hydrofluorocarbons, actually have no halogens, no chlorine and bromine in them. And so their destruction of ozone is essentially zero, which is a good endpoint if you're trying to protect the ozone layer and still keep refrigerators and air conditioners running. The trouble is that, which was understood in the early days, but it wasn't acted on. And that's that all of these gases, from CFCs to HFCs, are global warming gases, just like CO2 and methane. And so even though we would end up using HFCs in our conditioners, for example, the release of those compounds wouldn't be destroying ozone, but would be contributing to climate change. And then that didn't seem like a good endpoint as climate became much more in our consciousness. And as you pointed out, this led to the Kigali Amendment in 2016 that said, yeah, we shouldn't be investing in compounds that are really high global warming gases. And so it was really a phase down of a handful of the most potent of these gases is what Kigali put in place. And it's just starting up now in terms of the provisions starting to make a difference. And so this shows the power of the Montreal Protocol, that it didn't start out as a climate treaty, but it is today. It's an ozone and a climate treaty. And if you look at the preamble of the Vienna Convention that brought about the Montreal Protocol, the word climate is there. So it was kind of sleeping for a couple of decades, and now it's part of the protocol. And then, Jesse, what I was just saying, the three dimensions of the protocol: multilateral, fully funded, legally binding. The action of the protocol to adopt and enter into force the Kigali Amendment is the first such climate legislation, if you'll have it, in the world. It's the only body that has brought about legally binding controls on global emissions of greenhouse gases. This is often not recognized. And of course, controlling HFCs isn't going to solve our climate problem, but it's a component of it. And if you look at the projections of HFC use as the developing world became developed, it was a real threat if we let this go on for a couple of decades. And so this was the leverage, the scientific leverage or perspective that the scientists brought to the protocol, raising the flag as we did in 2009, and actually said, look at these projections, the actual use by countries and how it all adds up. And so we actually dodged a bullet, so to speak, meaning if we had blindly used HFCs globally for the next couple of decades, we would have been in a much tougher position in terms of trying to control our climate.
And that points in the big picture to the ultimate evidence of the success of the Montreal Protocol is that stratospheric ozone is starting to recover. The new report, the so-called quadrennial scientific assessment from your team, says that stratospheric ozone will recover roughly in the middle of the upcoming century. It depends upon whether you're looking at the Arctic, the Antarctic, or the middle latitudes. And it appears to be actual concentrations right now are starting to go upward. And I've heard the Montreal Protocol described as the most effective climate change treaty. In fact, given that the report says the Montreal Protocol appears to have avoided 1/2 to 1 full degree Celsius of warming by mid-century. That's impressive. Do you have anything to say about looking back on this process?
Well, I like that you draw that point out because, as I was just saying about HFCs, we've avoided significant climate change in our future by phasing down those chemicals now. So when the Montreal Protocol restrictions on CFCs started to take hold, the abundance of those, the emissions of those compounds went down rather quickly. And so one can then do what we call the world avoided. And now that we're a couple of decades away from the inception of the Montreal Protocol, we can say, well, what would have been the case if we didn't do anything about these compounds? And that's what you're referring to, Jesse, is if you do that difference between the world avoided and where we are today, it's very substantial. And it's a credit to us and the protocol that we have recognized this, acted on it, and avoided this world that you could describe. And the reason some of the difference is so great is because of our insatiable appetite for these compounds. If you go back to the 80s, the growth rate, the use of these compounds was 2 to 3% a year, I think, at some points. And so this 1/2 degree that you talk about is really the extrapolation of what if we kept expanding our usage at 2 or 3% a year for decades? where would we be? And so goes in the credit column of the Montreal Protocol. And as my technical colleagues tell me, look, Dave, it's hard to overestimate the interest in these compounds, that there were plans, I don't know how far along they were, that every can of Coke or soft drinks sold in the world would have a little charge of CFCs embedded in the can. And so if you're in an inhospitable place where there's no refrigeration, or even in a sophisticated society, you pop the little lever. There's two levers, one that releases the refrigerant and gives your soft drink a rapid cool, and then the next one that opens it for you to consume. And so there were plans, as I've been told, to do this. And you can imagine if every soft drink can in the world, or half of them, had a charge of CFCs associated with it, non-poisonous, non-asphyxiant, it just kind of disappears into the atmosphere, we would have a very different world today. So that's why the world avoided is worth thinking about.
I want to shift gears here a bit, talk about another way in which ozone, stratospheric ozone, its recovery, its potential depletion intersect with climate change, as well as steer the conversation toward the other report that you were recently involved with. And this is the topic of solar radiation modification, or solar geoengineering, which is an area where my co-host, who is unfortunately unavailable today, have been involved in. He is a scientist, myself as a policy person. And just as background, solar radiation management or modification is a proposal to slightly block a small portion of incoming sunlight to artificially cool the planet to counter climate change. And the current ozone report, the 10th scientific assessment of stratospheric ozone, has a new chapter that relates to SRM. Can you say why that chapter was added and what it concludes?
Another good question, Jesse. So parties to the protocol give us terms of reference for topics they would like to see in the new assessments from our panel and the other panels. And it's a formal decision that you can find on the web. And this cycle for 2022, they asked us to consider how plans, proposals, possibilities for solar radiation modification involving changes in the stratosphere might impact stratospheric ozone. And this topic had been in the assessment before, more parenthetical, a paragraph, a subsection, where we acknowledged the possibility. But the discussion in the world is increasing, climate change impacts are increasing. It seemed timely from the point of view of the parties to talk about this. So we welcomed that and went about our business and created an author team that took this on. And the reasoning here is that if you look at the stratospheric ozone layer, it's actually quite vulnerable. It's a natural phenomenon where ozone is constantly being produced and lost in the stratosphere due to natural cycles, but the average value is what we have today that's large enough to protect us. And so it is easy to disturb that. As we know from ozone depleting substances in our refrigerator, we can cause the ozone layer to be depleted. The simple reasoning, again, is if we decided to somehow change the aerosol population in the stratosphere a sufficient magnitude to scatter back enough sunlight to meaningfully cool the planet, it seems an unavoidable conclusion that we would probably do something to stratospheric ozone, because the chemical sensitivity that fragile layer has. And indeed, that's the case. We show that in this chapter. Of course, we don't develop any research. We're basically pulling research in from the community. So the community long known this. So that's the importance of the chapter, and that's how it came about.
So the leading proposed method of solar radiation modification is to inject aerosols, tiny particles, into the stratosphere, almost to the point that that's almost synonymous with SRM. I'm curious if you can dive a little bit more into the specifics of the potential range of impacts of a realistic implementation of stratospheric aerosol injection, SRM, might be. I imagine that, like so many other impacts of SRM, the answer is, well, it would depend upon the implementation regime. How much is injected, what latitude, at what time of year, of which substance, and so forth. In particular, I'm curious about evidence around which substances used. So much research has been around sulfates, sulfur dioxide, which we know the most about because that's the substance that volcanoes emit and naturally cool the planet. And by my understanding, also naturally deplete some stratospheric ozone. So what's sort of the range of outcomes if we were to do a little bit of careful SRM or a lot of reckless SRM in terms of stratospheric ozone?
Good question, Jesse. So your first point is extremely well taken, that this is a controversial topic in the world, as you know. And the controversy is enhanced by not having a shared frame of reference. And you just listed off the dimensions of an SRM scenario: latitude, abundance, season, altitude, the actual compound itself. And so we call this a scenario. We have to have shared scenarios to be able to really have meaningful, first of all, scientific discussions, and then grow into meaningful policy discussions. And we mentioned the IPCC before, and that's tremendous template that the IPCC has made substantial investments in describing scenarios, plausible scenarios for the future regarding climate change gases and climate change impacts. And it spans the range of possibility from not doing anything to having aggressive mitigation. And so across the board, whether you are looking at individual aspects of the climate system or you're running Earth system models, those scenarios, the baseline, they're the foundation of your studies. And so right now we lack that in this climate intervention world. And it's hurting us now because we can't have coherent conversations about this. And there are a lot of opinions about climate intervention that aren't coming from the science side. They're coming from the social side, the ethics, the impact side, which is okay, but adds to confusion because everybody's looking at the elephant from their direction or making assumptions that are hidden, that in order to really talk it through, they have to become unhidden. So that's my personal interest, is in fostering the development of such scenarios that will stabilize the conversation for both scientists, policymakers, and other interested parties. And concerning sulfate, you're right, nature has shown us how to cool the planet through explosive volcanic eruptions that enhance the stratospheric aerosol layer temporarily for a few years. Mount Pinatubo in the Philippines was the last example in 1991, which cooled the planet the next year by 0.5 degree centigrade or so. And so this demonstrates the basic feasibility of cooling the planet this way. But there may be other compounds that we could put in the stratosphere that don't come from volcanoes that would also be effective and might have less side effects, starting with changes to stratospheric ozone. The whole topic of SRM is full of uncertainties, and the kind of compound or material you would use is certainly one of those. And it's probably the most uncertain because we haven't done the scientific homework on trying to understand the physics and chemistry and dynamics well enough to actually have a credible opinion about other materials. But you bring up the point that part of climate intervention research, the more serious we get about it, the more serious we should be about thinking beyond sulfate.
The other report that you were involved in recently was, in fact, a more general scientific assessment of SRM, not just stratospheric aerosol injection and not just related to its potential impacts on the ozone layer. But this is a recent, fairly short report that was published by UNEP, the UN Environment Program, called One Atmosphere. And this, to my knowledge, is the first scientific assessment, in-depth scientific assessment, outside of the few pages the IPCC would dedicate, on SRM from an intergovernmental organization. In that context, what can you say about the background of this report? What was its origin? And did that come out of the 2019 conversations at UNEP's governing body, where a proposal to review SRM and carbon removal stalled?
Well, first of all, the One Atmosphere document I would call a report, not an assessment. There's just a handful of scientific references, citations in that document. So it's not meant to really make a scientific case per se. I consider it more of a narrative, an organized discussion on this topic. It's question and answer based. So it's trying to draw the reader into this narrative, trying to pose and then answer the important questions that come up when you think about this topic. And you're right, it's in the UNEP framework, which means it's at the United Nations level. And so it has a high perch to address all the countries in the world on this topic. I can't speak to the backstory of how this report came about because I wasn't involved. And it may be a complex, kind of twisty road where we got to this point. Well, one of the themes and the objectives of this report was to inform the Secretary General on this topic. So that was kind of our audience as an author of this report. What would you say to the Secretary General who said, I would like to know more about this topic and how it might be of interest in my world as Secretary General? And as you point out, it's short. It's not meant to be everything, but it's pretty substantial. And there really is no other document of its kind in the world today that has the imprimatur of the United Nations and UNEP. And it wasn't reviewed. The author team basically represents a diversity of opinions and backgrounds. And we came together to achieve as much consensus as we could as to what questions would you pose and how would you answer them, noting that nothing is the final word and it would help catalyze further discussion. And in particular, we make some very specific recommendations to the United Nations bodies, and that gives those bodies an entry point of departure for doing more, taking what we wrote and acting on it.
Yeah, I'd like to dive into at least a couple of those recommendations, time permitting. The first of which is a robust scientific review process for SRM by a global body. What form might that take? It doesn't specify which United Nations body might do that, and what process might catalyze it. What's the thinking behind the lack of specifics?
Yeah, we stopped short of making specific recommendations. We aren't members of these bodies. We're certainly familiar with them. And to me, the call for a scientific review process or assessment kind of transcends how you're actually going to do it. That, as I pointed out earlier, there's almost a desperate need for an assessment in order to stabilize and help direct and organize the discussions in the world on this topic, whether you're a scientist, policymaker, etc. But the reduction to practices always shows up at some point like, okay, we all agree we should do this. How and where are we going to do it? And again, we stopped short of doing that because it's not really in our wheelhouse and it's a difficult question. And we talked about IPCC and Montreal Protocol as really well-functioning bodies with really very valuable objectives, etc. But I think people who understand that pause and say, well, I'm not sure you would ask those two bodies to do the kind of assessment that you might want to have. And part of it is just kind of a swim lane argument that the Montreal Protocol, its mandate is to be a steward of the stratospheric ozone layer, which we have noted here. It would be affected by SRM in the stratosphere. But that's their swim lane. If you want to expand it and say, well, what about precipitation impacts? What about other means of SRM, etc.? That's really getting beyond their mandate. Similarly with IPCC, they could conceivably do this, but it's not obvious that that's necessarily the best place to do it. So this is pending. And as I said earlier, I'm hoping this report makes a very clear case for and a strong recommendation, which it does, for a review process and assessment, will motivate others who actually have the authority and the mandate and resources to do this to actually carry it out.
The second recommendation is a governance framework or multiple frameworks for possible small-scale outdoor SRM experiments and large-scale operational deployment. If I read between the lines, or in fact, I don't have to read between the lines, it's clear that there wasn't quite consensus about getting into some specifics here, especially in the case of the small-scale outdoor experiments. In your personal opinion, what might be the next step towards such governance frameworks?
So, Jesse, the word governance is a really important word with regard to SRM for at least two reasons. One is that there's such a diversity of opinion from a number of sectors and specialties about whether we should even do research SRM, and certainly whether we should conducting small scale experiments and for sure ultimately deployment. And so we just have to sort that out. We have to develop a community framework to do this. And the second reason is that, as the title of this report highlights, and this was very deliberate by the author team, we only have one atmosphere. And so whatever we do in that atmosphere, for example, if we were to change the stratosphere, we change everybody's stratosphere. We're not just going to change the stratosphere over the United States or Europe or Asia. We change everybody's stratosphere. And so it really behooves us then to have a governance process that takes into account everybody's interests and concerns and try and decide how to go forward. So just as with the assessment today doesn't really have a home. No one has stood up and said, yeah, let's do it here, and this is how we're going to do it. We all know pieces and parts of it because there are other assessments, but it hasn't coalesced to a plan. Same with governance. There is no standing up yet saying this is how we should do that. And so we're at a loss as a society because time is clicking by and we haven't started this difficult process.
And that seems to be a justification, the one atmosphere, that whatever is done to the atmosphere affects everyone's atmosphere. The justification for the final recommendation, conclusion section of this report, and that's a globally inclusive conversation of SRM should be promoted. Can you elaborate on what a global conversation might look like? Is this the public? Is this scientific research? Is it governance dialogue?
I think it's all of the above, and that's why it ended up on this list, because kind of intimated in my earlier remark that governance, of course, would be anchored by conversation and for conversation. And because of the complexity of this topic, the conversations would also be complex and would be multifaceted, so to speak. And in particular, as we call out in that recommendation, the Global South, that yes, it's one atmosphere and it covers all the countries, but we don't necessarily have equity after that. When you come together to create an assessment, those countries with substantial resources are able to participate more strongly and competently and are often leading it. And the Global South is struggling sometimes to have a voice at the table or to find a meaningful way to contribute even scientifically to this. So that's why we call this out, is this topic more than most really begs to have equity in terms of participation. If you're a developing country and you read about the Montreal Protocol and you look at the success of how it's managed ozone-depleting substances, you go, that's fine. I mean, I love the way the Montreal Protocol is serving my developing country without my participation, perhaps, because we don't have the resources to do that. But we absolutely applaud what they're doing and tell them full speed ahead. Where on the SRM world, that's not going to be the case for some of the developing countries, because they'll raise their hand and say, well, we're not sure that we want full speed ahead with SRM, and we'd like to be at the table to discuss it. So I think the burden on the process to create a globally inclusive conversation will be much greater than, say, it has been for the Montreal Protocol and protecting ozone.
Dr. Fahey, we conclude our podcasts typically with a question about optimism. So much of environmental science and environmental policy, especially in climate change, is sometimes not encouraging. But you have been involved deeply for much of your career in the greatest success of global environmental policy. In this context, what gives you optimism about the future?
Another good question. I have grandchildren, and so I can't not be optimistic about the future, their future in particular. And I think optimism should be our default approach when we're faced with what seems like unsolvable problems. So yeah, I'm optimistic both policy-wise and technology-wise and scientific, because there's so much tremendous horsepower, intellectual horsepower in the world, new ideas, young people who want to devote their careers to this, policymakers who we as scientists would say, yeah, they get it. We'd like to help them, move ahead on the policy world. So I have to be optimistic. It's not good to preclude the future and say, well, I know this isn't going to work. And I've read somewhere recently about someone conjecturing there's no way we would ever have a governance framework. It's impossible to think of a governance framework for this topic. This opinion you might have found in 1986, the year before the Montreal Protocol was adopted, saying there's no way you're going to get 197 nations to agree to regulate chemicals in their borders that affect the sectors and the quality of life in their country. And maybe there was. I wasn't reading that at that time. And so here you kind of pulled the rabbit out of the hat that we now have the most successful treaty in history. It's in its fourth decade. And so betting against the world in that respect, I'd like not to do that. I'd like to bet for them. And yeah, the climate problem is far more complicated than the ozone problem, but we succeeded with the ozone problem. And I would say today we have far more sophisticated tools, not only in communication, but in execution. And we have Chat GPT, we can ask the chat bot, what should we do about getting climate consensus? Anyhow, I'm playing with you a bit. I am optimistic, and I hope my grandchildren are part of the solution, as I'm sitting in my rocking chair.
Thank you. Our guest today has been Dr. David Fahey. David, thank you for your time.
Thank you, Jesse. I appreciate it.
Well, thanks for listening. Please rate or review us on Apple Podcasts and elsewhere, and consider supporting us on Patreon. That's patreon.com/challengingclimate.